Here's something worth thinking about as you settle in tonight. Right now, as you're lying there, perfectly still, maybe pulling the covers up a little, the ground beneath you is moving. Not in some poetic metaphorical sense. I mean literally moving. The actual solid earth under your building, under your street, under your whole city, is drifting across the surface of the planet at roughly the same speed your fingernails grow, a few centimeters a year. You'll never feel it. There's no vibration, no hum, nothing perceptible at all. But it's happening. It's been happening since long before there were people around to wonder about it. And it'll keep happening long after we're gone. And the story of how we figured that out, how human beings went from having absolutely no idea that the ground moves to understanding the entire mechanical system that reshapes the surface of our world. That's what we're going to talk about tonight, slowly. No rush, just one fascinating piece at a time. Let's start with something that almost everyone notices at some point, usually when they're a kid staring at a map on a classroom wall. Look at the east coast of South America and the west coast of Africa. They fit together, not perfectly, not like a jigsaw puzzle that snaps clean, but close enough that it's hard to unsee once you've noticed it. The bulge of Brazil tucks right into the Gulf of Guinea. The coastlines mirror each other in a way that feels like it can't be a coincidence. And people noticed this a long time ago. As early as 1596, a Dutch mapmaker named Abraham Ortelius, one of the great cartographers of the Renaissance, wrote in his geographical work that the Americas had been torn away from Europe and Africa by earthquakes and floods. He didn't have a mechanism, didn't have evidence beyond the shape of the coastlines, but he put the idea in writing. The Americas had once been attached, and something had ripped them apart. That was over 400 years ago, and then, basically, the idea just sat there. Nobody did much with it. It was a curiosity, a parlor observation, the kind of thing you'd mention at a dinner party and then move on. Because what could you really do with it? You couldn't prove it. You couldn't explain it. And honestly, the idea that entire continents could move seemed absurd. The ground is solid. Mountains don't walk. It felt like the kind of thing a child would say, not a serious scientific proposition. Fast forward about 300 years to the early 1900s, and we meet the person who would change everything, even though almost nobody believed him while he was alive. His name was Alfred Wegener, and his story is one of the great tragedies of science. A man who was fundamentally right about one of the biggest ideas in the history of geology, and who died without ever getting the credit he deserved. Wegener wasn't a geologist. That's the first thing you need to know about him, because it matters enormously for understanding why the scientific establishment treated him the way it did. He was a meteorologist, a weather guy. He was born in Berlin in 1880, studied astronomy and meteorology, and made his early reputation doing things like setting a world record for the longest continuous balloon flight. Him and his brother stayed aloft for over 52 hours in 1906, which was a serious feat of endurance and navigation. He went on expeditions to Greenland to study polar air circulation. He was tough, curious, and genuinely brilliant, but he was not a member of the geological club, and in the early 20th century. That mattered. Science was deeply tribal. Geologists studied rocks. Meteorologists studied weather. And if you were a weatherman, telling rock people that their entire understanding of the Earth's surface was wrong, you'd better have extraordinary evidence. What Wegener had was a collection of observations that, taken together, painted an incredibly compelling picture. It started with the coastlines, sure. The same thing Ortelius had noticed, but Wegener went much further. He looked at the geological formations on either side of the Atlantic and found that they matched. There were mountain ranges in Scotland and Scandinavia that were geologically identical to the Appalachian Mountains in eastern North America. Same rock types, same ages, same structural patterns. If you push the continents back together, those mountain ranges lined up perfectly, like a torn newspaper, where the print on both halves still matches across the rip. He found the same thing with rock formations in South America and Africa. Ancient cratons. Those are the oldest, most stable cores of continents that shared the same age and composition on both sides of the ocean. Then there were the fossils. This was maybe his most powerful evidence, and it's worth slowing down on because it's genuinely beautiful in its logic. There was a small reptile called Mesosaurus, a freshwater creature that lived about 300 million years ago. Mesosaurus fossils had been found in only 2 places on Earth: eastern South America and western Africa. Nowhere else. Now, this was a freshwater animal. It couldn't have swum across the Atlantic Ocean. So how did the same species end up on 2 continents separated by thousands of miles of salt water? The conventional explanation at the time was something called land bridges. The idea that there had once been thin strips of land connecting the continents, like natural causeways, and animals had walked across before the bridges sank beneath the waves. It sounds reasonable enough until you think about it carefully. You'd need an enormous amount of land to just disappear into the ocean floor, and there was no good mechanism for that. Wegener's explanation was simpler and more elegant. The 2 continents had been joined. The Mesosaurus had lived on one continuous landmass, and then that landmass had split apart. He found the same pattern with a fern called Glossopteris, whose fossils appeared in South America, Africa, India, Antarctica, and Australia, all the southern continents. And with a land reptile called Lystrosaurus, which showed up in Africa, India, and Antarctica. The distribution of these ancient organisms made no sense on a map of the modern world, but it made perfect sense if you pushed all the southern continents together into one giant landmass, which is exactly what Wegener proposed. In 1912, and then more fully in his 1915 book Die Entstehung der Kontinente und Oceane, The Origin of Continents and Oceans, Wegener laid out his theory. He called it continental drift. He proposed that all the continents had once been joined together in a single supercontinent which he called Pangaea, from the Greek for all lands, and that over hundreds of millions of years, Pangaea had broken apart and the pieces had drifted to their current positions. He even brought in climate evidence. He pointed to glacial deposits. the scratches and sediments left behind by ancient ice sheets, found in places that are now tropical, like India and equatorial Africa. Those regions couldn't have been glaciated where they sit today. But if they'd once been clustered near the South Pole as part of a larger landmass, the glaciation made sense. He found coal deposits in Antarctica, which meant that at some point in the deep past, Antarctica had been warm enough to support lush forests. He was assembling evidence from paleontology, geology, and climatology into a single, unified picture. And that picture said the continents move. The response from the scientific community was, to put it gently, hostile. And here's where you have to feel for the guy. Because the criticism wasn't entirely unfair, even though the conclusion was wrong. The geologists had a legitimate question, and it was devastating in its simplicity. What force could possibly move an entire continent? Wegener didn't have a good answer. He suggested that the continents plowed through the ocean floor like ships through water, driven by tidal forces from the moon and the centrifugal effect of the Earth's rotation. And the physicists and geologists ran the numbers and showed that those forces were nowhere near strong enough. Not even close. The tidal force required to push a continent through solid oceanic crust would be strong enough to stop the Earth's rotation in about a year. It was a non-starter. So they rejected the whole thing, not just the mechanism, the entire idea. The baby went out with the bathwater, and the rejection was often personal and ugly, the way scientific disputes sometimes are. The president of the American Philosophical Society called the theory utter damned rot. A prominent geologist said Wegener's method was to start with a conclusion and then hunt for evidence to support it, which is about the most damning thing you can say about a scientist. The British geologist Philip Lake said the theory was of the footloose type, in that it is not pinned down by a corpus of facts. At geological conferences, Wegener's ideas were openly mocked. And remember, he wasn't one of them. He was a meteorologist, an outsider. That made it easier to dismiss him. Wegener kept pushing, kept refining, kept publishing new editions of his book, but he never found the mechanism. He never answered the fundamental question of what moves the continents. And in November of 1930, on his third expedition to Greenland, Alfred Wegener died. He was 50 years old. He'd been resupplying a remote weather station on the ice cap, and on the return journey, in temperatures around -60 degrees Fahrenheit, his heart gave out. His body was found the following spring, carefully buried in the snow by his companion, who had also perished trying to make it back to the coast. Wegener was buried where he fell, on the Greenland ice sheet, and his grave has been slowly moving toward the sea ever since, carried by the flow of the glacier. There's something almost poetic about that. The man who said the Earth's surface moves, buried in ice that is itself in motion, his resting place drifting a little further each year. When Wegener died, continental drift was considered a fringe idea. Most geologists had moved on. The prevailing theory was that the Earth was slowly cooling and contracting like a drying apple, and the wrinkles on its surface were mountains and ocean basins formed by that shrinkage. It was tidy, it was intuitive, and it was completely wrong. But it would take another 30 years, an entirely new field of science, and a war that sent thousands of ships crisscrossing the ocean floor before anyone would figure out what Wegener had gotten right and what he'd gotten wrong, and more importantly, before anyone would discover the actual engine that drives the whole system. And that discovery started, of all places, with submarines. During the Second World War, the United States Navy needed to understand the ocean floor in unprecedented detail. Submarines were a decisive weapon, and knowing the topography of the seabed, where the ridges were, where the deep trenches lay, how sound traveled through different water layers, was a matter of life and death. So the Navy invested heavily in sonar technology and ocean mapping. And after the war ended, that technology and expertise didn't just disappear. It got handed to scientists. Oceanographers suddenly had tools that no one had ever had before. And what they found on the bottom of the ocean was nothing anyone expected. The ocean floor was supposed to be boring. That was the assumption. Geologists had imagined it as a vast, featureless plain. Maybe some accumulated sediment, some gentle rolling hills, but basically just a flat expanse of ancient rock sitting quietly under miles of water. And that made sense if you thought the Earth was a slowly cooling, contracting sphere. The ocean basins would just be the low spots, the places where the crust had sunk as everything shriveled. Simple, uninteresting, the kind of place you'd file away and never think about again. But that's not what the sonar showed, not even close. The person who first started making sense of what was down there was a woman named Marie Tharp, and her story is one of those cases where someone was in exactly the right place at exactly the right time, with exactly the right kind of mind, and still had to fight for years to be taken seriously. Tharp was born in 1920 in Ypsilanti, Michigan. Her father was a soil surveyor for the U.S. Department of Agriculture, and as a kid she traveled with him while he made maps. She grew up watching someone translate the physical world into lines on paper. That matters, because what she would eventually do, her life's work, was exactly that, except the physical world she mapped was 2 miles underwater, and no human eye had ever seen it. Tharp studied English and music in college, then got a master's in geology during the war. One of those moments when universities opened their doors to women because so many men were overseas. After the war, she ended up at Columbia University's Lamont Geological Observatory, working with a geologist named Bruce Heezen. Now, here's the thing about their partnership. Heezen went to sea. He collected data. He gathered the sonar readings, the depth soundings, the profiles of the ocean floor recorded by ships dragging instruments back and forth across the Atlantic. But women weren't allowed on the research vessels at that time. Tharp couldn't go, so she stayed in the lab, and her job was to take all of those thousands upon thousands of sonar readings and turn them into maps. She plotted depth measurements by hand, point by point, profile by profile, building up a picture of the Atlantic Ocean floor that no one had ever assembled before. And what emerged from those data points was astonishing. Running right down the center of the Atlantic Ocean roughly equidistant from the coastlines on either side, was an enormous mountain range. Not a small ridge, a mountain range. It stretched from the Arctic all the way down past the tip of Africa, thousands of miles long, with peaks rising over 10,000 feet above the surrounding ocean floor. This was the Mid-Atlantic Ridge, and it was one of the largest geological features on the planet, and nobody had known it was there. But that wasn't even the most interesting part. As Tharp plotted more and more profiles across the ridge, she noticed something. Right along the very crest of the ridge, running along its spine like a crack, was a deep valley, a rift, a gap. The mountain range wasn't just a mountain range. It was split open at the top, and when Tharp saw that rift valley, she immediately thought of one thing. This looks like a place where the earth is being pulled apart. If you had a crack running along the top of an underwater mountain range, it suggested that material was welling up from below, pushing the ridge higher, and then splitting as it spread to either side. It looked, in other words, like the ocean floor was moving, she told Heezen. And Heezen's first reaction was to dismiss it. He told her it looked too much like continental drift, and he reportedly said something along the lines of girl talk. That's a direct quote that Tharp herself recounted years later. He didn't want to be associated with Wegener's discredited idea. Nobody did. Continental drift was still in the early 1950s considered almost professionally embarrassing to support. So Tharp went back and checked her work. She replotted, she recalculated. The Rift Valley was still there. It wasn't an error. It wasn't an artifact of bad data. It was real. And then something else happened that changed Heezen's mind. A colleague named Howard Foster had been plotting the locations of earthquake epicenters in the Atlantic Ocean. And when Heezen laid Foster's earthquake map on top of Tharp's ocean floor map, the earthquakes lined up almost perfectly along the Rift Valley. The seismic activity was concentrated right there, right along that crack at the top of the ridge. That's not a coincidence. That's a pattern. And patterns in nature mean something is happening. The Earth wasn't just passively sitting there with a crack in it. The crack was active. Things were moving. Things were breaking. Energy was being released along that line over and over and over again. Heezen came around, and together he and Tharp continued mapping, extending their work beyond the Atlantic. And here's what's wild. They found that the Mid-Atlantic Ridge wasn't just an Atlantic feature. It connected to ridges in the Indian Ocean, which connected to ridges in the Pacific, which connected back around. It was a single continuous system of underwater mountain ranges, winding through every ocean on Earth like the seam on a baseball's. The whole thing was something like 40,000 miles long. 40,000 miles of underwater mountains, all with rift valleys running along their crests, all seismically active. It was the longest mountain range on the planet, and it was almost entirely hidden beneath the waves. Think about that for a second. The most prominent geological feature on Earth, the single largest structure, was underwater, and humanity didn't know about it until the 1950s. We'd mapped the surface of the moon with telescopes before we knew what was on our own ocean floor. That should give you a sense of just how much the ocean had been hiding. Now, the mid-ocean ridge system was a huge clue, but it wasn't proof of anything by itself. You could look at that rift valley and suspect that the ocean floor was spreading apart. But you needed a mechanism, and you needed evidence that it was actually happening. This is where a geologist named Harry Hess enters the story. Hess was a professor at Princeton, but during World War II, he'd served as a Navy captain commanding a transport ship in the Pacific, and while his ship was crossing the ocean on various missions, Hess kept the ship's sonar running continuously, quietly collecting depth readings of the Pacific floor. He wasn't supposed to be doing science. He was supposed to be fighting a war, but he couldn't help himself. He was a geologist on a ship with a perfectly good echo sounder, and the ocean floor was right there beneath him, unmapped. So he mapped it, battle after battle, crossing after crossing, amassing an enormous collection of depth profiles almost as a side project. After the war, Hess went back to Princeton and spent years thinking about what he'd seen. And in 1962, he published a paper that changed everything. He was cautious about it. He actually called it an essay in geopoetry, as if to soften the blow, as if to say, look, I know this sounds speculative, but hear me out. What Hess proposed was this. The ocean floor is not permanent. It's not ancient. It's being continuously created at the mid-ocean ridges, where hot material from deep inside the Earth rises to the surface, cools, and forms new crust. That new crust then moves away from the ridge on both sides, like a slow conveyor belt, carrying everything on top of it, sediment, water, eventually continents, along for the ride. And when that crust reaches the edge of an ocean basin, it plunges back down into the Earth's interior at deep ocean trenches. The whole thing is a cycle. Crust is born at the ridges, travels across the ocean floor, and is consumed at the trenches. He called it seafloor spreading. This was the mechanism Wegener never had. Wegener had imagined continents plowing through the ocean floor like ships through ice, and that was physically impossible. The forces didn't work. But Hess was saying something different. The continents weren't plowing through anything. They were passengers. They were riding on top of the ocean floor as it moved, carried along by this great conveyor belt of creation and destruction. The continents didn't need their own driving force. They just sat on plates of crust that were already in motion. And here's the beautiful thing about Hess's idea. It was testable. If the ocean floor really was spreading outward from the ridges, then the crust nearest the ridge should be the youngest, and the crust farther away should be progressively older. You should be able to measure this. The sediment on the ocean floor should be thinnest near the ridges, where the crust is brand new and hasn't had time to accumulate much, and thicker farther away, where it's been collecting for millions of years. And that's exactly what drilling expeditions later confirmed. The pattern was unmistakable. The ocean floor was young near the ridges and old near the continents. The oldest ocean floor anywhere on Earth turned out to be only about 200 million years old, which sounds like a lot until you remember that the Earth itself is 4.5 billion years old. The ocean floor is being recycled. It's being created and destroyed on a time scale that, geologically speaking, is remarkably fast. But the most elegant confirmation of seafloor spreading came from an unexpected direction: magnetism. And this is one of those stories where two separate lines of evidence crash into each other, and suddenly the whole picture snaps into focus. You see, the Earth has a magnetic field. You know this. It's what makes compasses work, what creates the northern lights, what shields us from solar radiation. But here's something you might not know. The Earth's magnetic field flips every so often, and by every so often I mean every few 100,000 to few million years, on an irregular schedule. The magnetic north and south poles swap places. A compass that points north today would have pointed south 780,000 years ago. We call these magnetic reversals, and they leave a record in volcanic rock. When lava cools and solidifies, the iron minerals in it align with whatever magnetic field exists at that moment, like tiny compass needles frozen in place. So if you can read the magnetic signature of a rock, you can tell which direction the Earth's field was pointing when that rock formed. In the early 1960s, researchers towing magnetometers behind ships, essentially dragging magnetic sensors across the ocean floor, started noticing something peculiar. The magnetic readings weren't uniform. They showed a striped pattern, alternating bands of rock with normal magnetic polarity and reversed magnetic polarity, running parallel to the mid-ocean ridges, and the pattern was symmetrical. If you looked at the stripes on one side of the ridge, they were a mirror image of the stripes on the other side: normal, reversed, normal, reversed. The same sequence, the same widths, reflected perfectly across the ridge axis. Think about what that means. If new rock is being created at the ridge, cooling and locking in the current magnetic field, and then splitting apart and moving away in both directions, you'd get exactly this pattern. Each time the Earth's field flips, the new rock forming at the ridge records the new polarity, and the older rock with the previous polarity has already moved away. It's like a tape recorder running in two directions at once, printing the same magnetic history on both sides of the ridge. The symmetry was the smoking gun. Two British researchers, Fred Vine and Drummond Matthews, published this interpretation in 1963, building on work by Lawrence Morley, a Canadian who had independently reached the same conclusion, but whose paper had been rejected by two journals. One reviewer reportedly called it the kind of thing you'd discuss at a cocktail party. Morley's bad luck with peer review is one of those small tragedies of science. He was right, and he was first. But Vine and Matthews got the credit because their paper made it to print, and with those magnetic stripes, the debate was essentially over. Seafloor spreading was real. The ocean floor was a moving conveyor belt, just as Hess had proposed. And if the ocean floor was moving, then the continents sitting on top of it were moving too. Wegener had been right about the what. The continents do drift, even though he'd been wrong about the how. It had taken more than 40 years, a world war, the invention of new instruments, and the patient work of people like Tharp and Heesen and Hess and Vine and Matthews to prove it. But the Earth's surface was in motion. That was now established fact. What wasn't yet fully worked out, though, was the bigger picture. Seafloor spreading explained what was happening at the mid-ocean ridges, but the Earth is a closed system. If new crust is being created somewhere, old crust has to be going somewhere else. Hess had talked about trenches, about crust diving back down into the interior. But how did all of this fit together? How many pieces was the Earth's surface broken into? How did they interact at their edges? And what exactly was driving the whole thing from below? Those questions were about to be answered in a burst of scientific activity in the mid-1960s that would pull everything together into a single, unified framework. A theory comprehensive and so well supported that it would become one of the foundational ideas in all of Earth science. And the key to that framework was something that had been staring geologists in the face for decades, hiding in plain sight in the global pattern of earthquakes and volcanoes. Because if you take a map of every major earthquake recorded in the 20th century and plot them all as dots, something incredible jumps out at you. They're not scattered randomly. They're not spread evenly across the planet. They cluster. They form lines. Narrow, sharp, unmistakable lines that snake across the globe. And those lines carve the Earth's surface into distinct pieces, like the seams on a soccer ball. That pattern had been visible in seismological data for years, but it took a particular kind of thinking, the kind that only becomes possible once you've accepted that the surface is moving, to see those lines for what they really are, boundaries. Edges, the places where one rigid piece of the Earth's outer shell meets another. And this is where a Canadian geophysicist named J. Tuzo Wilson enters the story. And honestly, Wilson is one of those figures who deserves to be far more famous than he is. By the early 1960s, Wilson was already in his 50s, a well-established professor at the University of Toronto, and he'd spent most of his career as a fairly conventional geologist. He'd actually opposed continental drift for years. But when the evidence from the ocean floor started piling up, the magnetic stripes, the age patterns, the ridge system, Wilson didn't dig in and defend his old position. He changed his mind, and then he didn't just accept the new ideas. He pushed them further than anyone else had. In 1965, Wilson published a paper that introduced a concept so elegant and so necessary that it became one of the cornerstones of the whole theory. He proposed a new type of geological fault that he called a transform fault. Now, let me explain why this mattered so much, because it's one of those things that sounds technical but is actually beautifully simple once you see it. Picture the mid-ocean ridge, that long, underwater mountain chain where new crust is forming. If you look at it on a map, it doesn't run in one smooth, continuous line. It's offset. It zigzags. Every so often, the ridge is cut by a perpendicular fracture, and the ridge picks up again on the other side, shifted sideways by tens or even hundreds of miles. Geologists had noticed these fractures before and assumed they were ordinary faults, places where the ridge had been broken and displaced by some sideways force. But Wilson realized something different. He realized the motion along those fractures wasn't what everyone assumed. The two sides of each fracture weren't sliding in the direction you'd expect if the ridge had simply been offset. They were sliding in the opposite direction, and only between the two offset ridge segments. Beyond those segments, the motion stopped. Think about that for a second. If you have two conveyor belts sitting side by side, both creating new material at their centers and pushing it outward, the strips of belt between the two centers are moving toward each other or past each other, even though the belts themselves are doing the same thing. The fault isn't breaking the ridge apart. The ridge segments were always offset, and the transform fault is just the natural consequence of two adjacent pieces of spreading crust sliding past each other. Wilson saw this, and it was a completely new kind of plate boundary. Not one where crust is being created, not one where crust is being destroyed, but one where two plates are simply grinding sideways past each other. And here's the thing that made this more than just an academic insight. Wilson pointed out that the San Andreas Fault in California is exactly this kind of boundary. It's a transform fault. The Pacific Plate and the North American Plate are sliding laterally past each other, and that motion is what causes the earthquakes that Californians live with every day. So suddenly, this abstract oceanic concept had a very real, very terrestrial application. The ground under Los Angeles and the ground under San Francisco are on different plates, moving in different directions, and the San Andreas is the seam between them. Wilson also contributed something else that was crucial to the emerging framework. He was one of the first to clearly articulate the idea that the Earth's surface is divided into a finite number of rigid plates, and that essentially all the geological action, the earthquakes, the volcanoes, the mountain building, happens at the boundaries between those plates. The interior of each plate is relatively quiet, relatively stable. It's the edges where things get dramatic, and this is the key conceptual leap that turned a collection of separate observations, seafloor spreading, subduction, transform faults, into a unified theory. Plate tectonics. The name itself comes from the Greek word tekton, meaning builder or carpenter. And it's a fitting name because the theory describes how the Earth's surface is constantly being built, rearranged, and recycled. Now, the formal synthesis happened remarkably fast. In 1967 and 1968, three separate groups of scientists independently worked out the mathematical framework for plate tectonics on a sphere. Dan Mackenzie and Robert Parker at Cambridge published a paper in late 1967 showing how you could describe the motion of rigid plates on a spherical surface using a principle from geometry, Euler's theorem, which says that any movement of a rigid body on the surface of a sphere can be described as a rotation around some axis. Jason Morgan at Princeton presented similar work, actually slightly earlier, at a conference in 1967, though his full paper came out in 1968, and Xavier Le Pichon, a French geophysicist, took the work further by dividing the entire Earth's surface into 6 major plates and computing their relative motions. Just like that, in the space of about a year, the theory went from a qualitative idea to a rigorous, mathematical, testable framework. You could now calculate how fast any plate was moving relative to any other plate, predict what should be happening at their boundaries, and check those predictions against real data. And the predictions matched beautifully. So let's talk about those plates, because this is where the theory becomes something you can actually feel and visualize. The exact number depends on how you count. The major ones are pretty well agreed upon, but there are also smaller plates and microplates that people argue about. The big ones, though, the ones that carry most of the Earth's surface, number about 15. You've got the Pacific Plate, which is the largest and is almost entirely oceanic. It's the floor of most of the Pacific Ocean, and it's moving northwest relative to its neighbors. The North American Plate carries not just North America, but also the western half of the Atlantic Ocean floor, all the way to the mid-Atlantic ridge. The South American Plate, same idea on the southern side. The Eurasian Plate is enormous, stretching from the mid-Atlantic ridge all the way across Europe and most of Asia. The African Plate carries Africa and a good chunk of the surrounding ocean floor. The Antarctic Plate sits at the bottom, surrounded by spreading ridges on almost all sides. The Indo-Australian Plate, which some scientists now argue should be considered two separate plates, the Indian and the Australian, carries the Indian subcontinent, Australia, and the ocean between them. Then you've got smaller but still significant ones. The Nazca Plate in the Eastern Pacific, the Caribbean Plate, the Philippine Sea Plate, the Arabian Plate, the Juan de Fuca Plate, off the coast of the Pacific Northwest, the Scotia Plate near Antarctica, the Cocos Plate off Central America. And here's what's really satisfying about this picture. Once you know where the plates are and which direction they're moving, the entire pattern of earthquakes and volcanoes on Earth just makes sense. The Ring of Fire, that famous horseshoe of volcanic and seismic activity around the Pacific Ocean, is simply the boundary of the Pacific Plate, where it's colliding with and diving beneath the plates around it. The earthquake zone that runs from the Mediterranean through Iran and the Himalayas to Southeast Asia. That's the collision boundary between the Eurasian Plate and the African, Arabian, and Indian plates. The volcanoes of Iceland? That's the mid-Atlantic ridge poking above sea level, right where the North American and Eurasian plates are pulling apart. Every major earthquake zone on Earth lines up with a plate boundary. Every major volcanic chain either sits on a plate boundary or can be explained by a related mechanism. The theory doesn't just describe what's happening. It explains why it's happening, where it's happening. Now, the boundaries themselves come in three basic flavors, and we've actually already touched on all of them without quite naming them this cleanly. Divergent boundaries are where plates pull apart, the mid-ocean ridges. New crust is created here as magma wells up from below to fill the gap. Convergent boundaries are where plates push together, and what happens depends on what kind of crust is involved. If oceanic crust meets continental crust, the denser oceanic crust dives underneath in a process called subduction, creating deep ocean trenches, volcanic arcs, and powerful earthquakes. The Andes Mountains exist because the Nazca Plate is subducting beneath the South American Plate. If two oceanic plates converge, one subducts beneath the other, forming island arcs like Japan or the Mariana Islands. And if two continental plates collide, well, neither one wants to subduct because continental crust is too buoyant, too thick, too light to be easily pushed down into the mantle. So instead, the crust crumples. It folds and thickens and pushes upward. And that's how you get the Himalayas. India, riding on its plate, has been slamming into Asia for roughly 50 million years, and the crumple zone between them has been shoved skyward into the tallest mountains on Earth. Mount Everest exists because of a plate collision. The rock at its summit is limestone that formed on an ancient seafloor. Marine fossils have been found near the peak, creatures that lived in a shallow ocean that no longer exists, lifted almost 9 kilometers into the sky by the slow, relentless force of tectonic convergence. And then there's the third type, transform boundaries, Wilson's contribution, where plates slide past each other laterally. The San Andreas is the most famous, but there are others. The Alpine Fault in New Zealand, the Dead Sea Transform in the Middle East, the North Anatolian Fault in Turkey. These boundaries don't create or destroy crust. They just accommodate the geometry of plates moving in different directions on a curved surface. So by the late 1960s, this framework was in place, and it was extraordinary. For the first time in the history of geology, there was a single unifying theory that explained mountain building, volcanism, earthquakes, the shape of ocean basins, the distribution of fossils, the pattern of climate zones in the geological record, all of it. It was geology's equivalent of what Darwin's theory of evolution had been for biology. A framework that made everything else make sense. But there was still one enormous question hanging over the whole thing, the same question that had doomed Wegener half a century earlier. What drives it? What force is powerful enough to move entire continents, to push plates thousands of miles across the surface of the Earth? Hess had suggested convection currents in the mantle, great slow-motion circulation cells of Hawk, rising, spreading, cooling, and sinking. And that idea was broadly right. But the details turned out to be far more complicated and far more fascinating than anyone initially imagined. Because the engine that drives plate tectonics isn't one simple mechanism. It's a combination of forces, and understanding them requires you to think about what's happening not just at the surface, but hundreds of miles beneath your feet, in a realm of rock that behaves in ways that seem almost impossible until you really sit with them. Because the rock down there, and this is the part that bends your mind a little, is simultaneously solid and flowing. Not liquid, not molten, except in very specific limited pockets. Solid rock, and yet it moves, it creeps, it convects. Over thousands and millions of years, it circulates like an impossibly slow fluid. And that seeming contradiction is the key to everything. Let's talk about that for a second, because it's one of those ideas that sounds wrong the first time you hear it. You think of rock as the definition of something that doesn't move. You knock on a granite countertop, and it's about as solid as anything gets. But solidity is a matter of time scale. Think about glaciers. A glacier is solid ice. You could stand on it, chip at it with a pick. And yet glaciers flow downhill under their own weight, sometimes meters per day. Ice is solid, but given enough stress over enough time, it deforms and moves like a very thick fluid. Now imagine something similar, but orders of magnitude slower, happening with rock at temperatures of 1,000 degrees or more, and pressures that are almost incomprehensible, hundreds of thousands of atmospheres. Under those conditions, deep inside the Earth, solid silicate rock deforms plastically. It doesn't crack and break the way it would at the surface. It creeps. Mineral grains slowly rearrange themselves. Atoms diffuse across crystal boundaries, and the whole mass gradually, almost imperceptibly, flows. We're talking about rates of maybe a few centimeters per year, roughly the speed your fingernails grow. That's the pace of the mantle's great convective engine. And here's the thing. Even at that glacial pace, over tens of millions of years, the cumulative motion is enormous. A few centimeters a year for 100 million years is thousands of kilometers. That's how an ocean opens. That's how India traveled from the southern hemisphere to crash into Asia. Fingernail speed, world-changing distance. So the mantle convects. Hot material rises, cooler material sinks. And this circulation is ultimately driven by heat. But where does the heat come from? Two main sources, and they're both fascinating. The first is primordial heat. Heat left over from the formation of the Earth itself about 4.5 billion years ago. When the planet was assembling from the solar nebula, all those collisions between rockers converted kinetic energy into thermal energy. The impact that formed the moon alone, a collision with a Mars-sized body called Theia, roughly 4.5 billion years ago, would have melted most of the Earth's surface into a magma ocean. Some of that ancient heat is still trapped deep inside, slowly leaking outward. The second source is radioactive decay. Elements like uranium-238, thorium-232, and potassium-40 are scattered throughout the mantle and crust. And as their atoms decay, they release energy, not a lot from any individual atom, but multiplied across the entire volume of the Earth's interior, it adds up to an astonishing amount of heat. Something like 20 terawatts of power, continuously, just from radioactive decay. Together, these two heat sources keep the mantle hot enough to convect, and that convection is the fundamental engine. But, and this is where the story gets richer, saying convection drives the plates is a bit like saying combustion drives a car. It's true, but it doesn't tell you about the transmission, the wheels, the friction with the road. The actual forces that act on tectonic plates are more specific, and geophysicists have identified several that work together, sometimes reinforcing each other, sometimes competing. The first, and probably most important, is something called slab pull. Remember subduction zones. Those places where an oceanic plate dives beneath another plate and plunges into the mantle? Well, when a plate subducts, the leading edge sinks into hotter, less dense mantle material. But the subducting slab itself is old, cold oceanic lithosphere. It's cooled over millions of years as it traveled away from the mid-ocean ridge where it was born. Cold rock is denser than hot rock, so that sinking slab is heavier than the surrounding mantle, and gravity pulls it downward. And because the slab is still attached to the rest of the plate at the surface, it drags the whole plate along behind it, like a heavy tablecloth sliding off a table, pulling the rest of the cloth with it. That's slab pull. And the numbers suggest it's the dominant force. Plates that have large subducting edges, the Pacific plate, for instance, tend to move faster than plates without them. The Pacific plate moves at roughly 7 to 10 centimeters per year, which is fast by plate tectonic standards. The African plate, which has very little subduction happening around its edges, moves at only about 2 centimeters per year. That correlation is strong evidence that slab pull is doing most of the work. The second force is ridge push, and it operates at the other end of the plate, at the mid-ocean ridges. When hot mantle material rises at a divergent boundary and creates new crust, it also creates a topographic high. The ridge itself stands 2 to 3 kilometers above the surrounding ocean floor. The newly formed lithosphere is hot, buoyant, and elevated. As it cools and moves away from the ridge, it becomes denser and sinks lower. So there's a gravitational gradient. The plate is literally sliding downhill away from the ridge, very slowly, pushed by its own elevated weight. Ridge push is real, but it's generally considered weaker than slab pull, maybe only a third to a quarter as strong. Still, it contributes, especially for plates that don't have a subducting edge to do the heavy pulling. And then there's a third force that's been debated for decades, basal drag or mantle drag. This is the original Hess idea, that convection currents in the mantle flow beneath the plates and drag them along, the way a conveyor belt carries objects sitting on top of it. And the truth is, this one is complicated. In some cases, mantle flow beneath a plate might indeed be pushing it in the direction it's already moving, adding to the driving force. But in other cases, the mantle flow might actually be going in a different direction than the plate, which means it's acting as a resisting force, a kind of friction slowing the plate down. Whether basal drag helps or hinders depends on the specific plate and the specific pattern of mantle convection beneath it. It's not a simple conveyor belt. It's more like a plate surfing on a complex, three-dimensional flow field that varies from place to place. Now, you might be thinking, how do we know any of this? How can we possibly figure out what's happening hundreds of kilometers below the surface? And this is where one of the most beautiful tools in all of geophysics comes in: seismic tomography. Think of it as a CT scan of the Earth. When an earthquake happens, it sends seismic waves radiating outward in all directions through the body of the planet. Those waves travel at different speeds depending on the temperature and composition of the rock they pass through. Hot rock slows them down slightly. Cold rock speeds them up by recording the arrival times of seismic waves at hundreds of seismograph stations around the world, and then running those measurements through sophisticated computer algorithms. Geophysicists can build three-dimensional maps of the Earth's interior, showing where the mantle is relatively hot and where it's relatively cold. And what those maps reveal is stunning. You can actually see subducting slabs in the tomographic images, great cold fingers of dense rock plunging down from the surface, some of them reaching all the way to the core mantle boundary, nearly 3,000 kilometers deep. The Farallon Plate, which used to occupy much of the eastern Pacific and has been subducting beneath North America for over 100 million years, most of it is gone from the surface now, unconsumed by subduction. But its remnants are still visible in tomographic images, lying deep in the mantle beneath the central United States. A ghost plate, still sinking, still affecting mantle flow long after its surface expression vanished. Think about that. A piece of ocean floor that hasn't existed at the surface for tens of millions of years is still down there, still falling, still influencing what happens above. And on the flip side, the tomographic images also reveal hot upwellings, broad plumes or columns of anomalously warm mantle material rising from deep within the earth, some apparently originating from just above the core mantle boundary. These are the mantle plumes that many geophysicists believe are responsible for hotspot volcanism. Places like Hawaii Yellowstone, Iceland, Reunion Island. Hotspots are volcanic centers that don't sit on plate boundaries. They seem to exist in the middle of plates, which puzzled everyone when plate tectonics was first being worked out. Why would you have a volcano in the middle of the Pacific Plate, thousands of kilometers from the nearest plate boundary? J. Tuzo Wilson, yes, the same Wilson who gave us transform faults, proposed in 1963 that hotspots are fed by deep, relatively stationary sources of heat in the mantle. As a plate moves over one of these sources, it gets a chain of volcanoes, each one active for a while, and then carried away from the heat source, going extinct as a new volcano forms behind it. The Hawaiian Island chain is the textbook example. The Big Island of Hawaii, at the southeastern end, is the youngest and most volcanically active. Moving northwest along the chain, the islands get progressively older. Maui, Molokai, Oahu, Kauai, and beyond Kauai, the chain continues as a string of submerged seamounts stretching thousands of kilometers to the northwest, getting older and older, the oldest ones dating back over 80 million years. The chain even has a sharp bend in it, the Hawaiian Emperor Bend, where the direction of Pacific Plate motion changed around 47 million years ago. It's like a track record of plate motion written in volcanic rock on the ocean floor. In 1971, Jason Morgan expanded Wilson's idea into a full theory of mantle plumes, narrow columns of hot rock rising from the deep mantle, perhaps from the very boundary between the mantle and the outer core, a turbulent layer sometimes called the D double prime layer, sitting about 20,900 kilometers below the surface. Morgan proposed that these plumes are a separate mode of convection from the broad circulation that drives plate tectonics, a kind of secondary system, like bubbles rising in a pot of very thick soup. The plume hypothesis has been debated vigorously ever since. Some geophysicists see clear evidence for deep plumes in seismic tomography. Others argue the tomographic images are ambiguous, that the resolution isn't good enough, that some hotspots might be caused by shallower processes, cracks in the lithosphere, or small-scale convection in the upper mantle. The debate is genuinely unresolved for many proposed hotspots, though for a few, Hawaii, Iceland, maybe a handful of others, the evidence for a deep mantle source is fairly strong. And this is one of the things I find most beautiful about this whole story. Plate tectonics as a framework was essentially established by the late 1960s, but the details of the engine, the exact nature of mantle convection, the relative importance of slab pull versus ridge push versus mantle drag, the existence and depth of plumes, the role of water in weakening rock and enabling subduction. These questions are still being actively investigated right now. The theory isn't static. It's a living framework, being refined and deepened every year by new seismic data, new computer simulations that model mantle flow in 3 dimensions, new mineral physics experiments that recreate deep earth pressures in the laboratory using diamond anvil cells. There's a whole world of research happening at the boundary between what we know and what we're still figuring out. And it connects to something that might surprise you. The question of whether plate tectonics is unique to Earth, or whether it happens on other worlds too. Because as far as we can tell, Earth is the only planet in our solar system that has plate tectonics in the way we've been describing. This grand system of rigid plates sliding around, diving beneath one another, pulling apart, grinding sideways. And that's a genuinely strange thing when you think about it. We have 8 planets, dozens of moons, and only one body, where the surface is broken into these mobile pieces that constantly recycle themselves. So why Earth? What makes our planet special? Let's start with what we see elsewhere, because the contrasts are really illuminating. Take Venus. Venus is almost the same size as Earth, almost the same density, probably has a similar internal composition. If any planet should have plate tectonics, it's Venus. And yet, when the Magellan spacecraft mapped the Venusian surface with radar in the early 1990s, what it found was a world with no mid-ocean ridges, no subduction trenches, no long transform faults. The surface of Venus is geologically young, maybe 500 to 700 million years old on average, which tells you something dramatic happened relatively recently in geological terms. But it doesn't show the telltale signatures of ongoing plate tectonics. Instead, Venus seems to have what some scientists call a stagnant lid. The entire surface is one single plate, one unbroken shell, and heat escapes from the interior not through the elegant conveyor belt system we have on Earth, but through volcanic eruptions, through localized upwellings, and possibly through catastrophic resurfacing events where the whole lid becomes unstable and overturns all at once. Imagine the entire crust of a planet just giving way, sinking into the mantle more or less globally, and then a new surface forming from fresh lava. It's a dramatic image. Some researchers think Venus goes through these every few 100 million years, which would explain the SERP why the surface is relatively uniform in age. But it's not plate tectonics. It's something else entirely. So, what's different about Earth? Here's where it gets really interesting, and it connects back to something we touched on earlier: water. You might remember that water plays a role in weakening rock and enabling subduction. Well, that turns out to be one of the most critical factors in the whole story. Earth has oceans. Venus doesn't. And it's not just that water makes the surface slippery, or something simplistic like that. Water gets carried down into the mantle at subduction zones, locked inside the crystal structures of hydrated minerals in the oceanic crust. When that water-bearing rock descends and heats up, the water is released, and it fundamentally changes the properties of the mantle rock around it. Water lowers the melting point of rock. It lowers the viscosity. It makes the mantle weaker and more able to flow. Some researchers argue that without water cycling through the mantle, the asthenosphere, that weak, partially molten layer beneath the plates, might not be weak enough to allow plates to slide over it. The whole system might seize up. And there's another piece to this puzzle. On Earth, oceanic crust is made of basalt, which is relatively dense. When it gets old and cold, it becomes denser than the mantle beneath it, and that density difference is what allows subduction to initiate. The plate can sink, but the initiation of subduction is actually one of the hardest things to explain in plate tectonics. Even on Earth, starting a new subduction zone is incredibly difficult. The lithosphere is strong. It resists bending. You need some combination of forces. Maybe a pre-existing weakness, a fracture zone, the weight of accumulated sediment, or the push from a nearby ridge to get that first slab to turn downward. On Venus, without water to weaken the crust and mantle, without the density contrast that oceanic crust provides, subduction may simply never get going. The lid stays stagnant. Mars tells a different story, but arrives at a similar place. Mars is much smaller than Earth, about half the diameter, roughly a tenth the mass. Smaller planets cool faster. Mars likely had a more active interior early in its history. There's some evidence, actually, that Mars might have had something resembling plate tectonics very early on, maybe in its first billion years. The Valles Marineris, that enormous canyon system stretching nearly 4,000 kilometers across the Martian surface, has been interpreted by some researchers as a kind of failed rift, a place where the crust began to pull apart, but the process never fully developed into a spreading system. The crustal dichotomy on Mars, where the northern hemisphere is low and smooth, while the southern hemisphere is high and heavily cratered, has also been explained by some models as the result of an ancient episode of something like plate tectonics, or a massive overturn event. But whatever happened, it stopped. Mars's interior cooled, the mantle became too viscous to convect vigorously, and the planet settled into a stagnant lid regime. Today, Mars is essentially geologically dead at the surface, at least in terms of large-scale tectonics. There might still be some residual heat, maybe even occasional Marsquakes. The InSight lander detected seismic activity, but the grand recycling system that Earth enjoys, gone if it ever truly existed. Now here's something that genuinely surprised the planetary science community. In 2005, The Cassini spacecraft was orbiting Saturn and turned its instruments toward Enceladus, a tiny moon only about 500 kilometers across, small enough to fit comfortably inside the borders of Arizona. And at the south pole of Enceladus, Cassini found geysers, enormous plumes of water vapor and ice particles shooting hundreds of kilometers into space. The surface around the South Pole was young, fractured, warm. Something was generating heat inside this little moon, and the cracks in the icy surface, nicknamed tiger stripes, looked for all the world like a tectonic feature. Now, nobody is claiming that Enceladus has plate tectonics in the way Earth does, but it shows that tectonic processes, the cracking, shifting, and recycling of a world's surface driven by internal heat, aren't limited to rocky planets. Icy moons can do it too, in their own way, driven by tidal heating from the gravitational flexing caused by their parent planet. And then there's Europa, Jupiter's ice-covered moon, where images from the Galileo spacecraft in the late 1990s revealed a surface that looks astonishingly like sea ice on Earth, fractured into plates that have shifted, rotated, and in some places appear to have spread apart with new ice filling the gaps, almost exactly like seafloor spreading at a mid-ocean ridge. Some researchers have proposed that Europa might actually have formed of ice tectonics, where plates of ice on the surface are created as spreading zones move apart and are destroyed at convergent boundaries where one ice plate dives beneath another. If that's true, it would be the closest thing to plate tectonics we've found anywhere besides Earth, just made of ice instead of rock, floating on an ocean of liquid water instead of a mantle of flowing rock. Think about what that means for a second. The same basic principle, a brittle outer layer broken into pieces, moved by convection in a fluid layer beneath, might be a more universal phenomenon than we thought, just expressed in different materials on different worlds. Earth does it with silicate rock over a slowly convecting mantle. Europa might do it with ice over a liquid water ocean. The physics is the same, even if the chemistry is completely different. But let's come back to Earth, because there's a question we haven't really addressed yet, and it's a big one. When did plate tectonics start on our planet? You might assume it's been running since the beginning, since Earth formed about 4.54 billion years ago. But that's actually one of the most hotly debated questions in all of Earth science right now. The honest answer is, we don't know for certain, and the estimates range enormously from as early as 4.2 billion years ago to as recently as about 1 billion years ago, depending on what evidence you look at and how you interpret it. Here's the difficulty. The very nature of plate tectonics destroys its own evidence. Oceanic crust gets subducted. It goes back into the mantle. The oldest oceanic crust on Earth today is only about 200 million years old in the Western Pacific. Everything older has been recycled. So if you want to find evidence of ancient plate tectonics, you have to look at continental rocks, because continents aren't subducted. They're too buoyant, too thick, too light to sink. They survive. And some continental rocks are incredibly old. The Acasta gneiss in northern Canada is about 4 billion years old. Zircon crystals found in the Jack Hills of Western Australia have been dated to 4.4 billion years ago. Tiny, nearly indestructible time capsules from an Earth that was barely 150 million years old. Some researchers have analyzed the chemistry of those ancient zircons and argued that they show signatures of water-rich, relatively cool conditions at the surface, conditions that might be consistent with something like subduction happening very early. Others look at the same data and see a world that was too hot, too chaotic, with a mantle too vigorous and a lithosphere too thin and weak to form rigid plates. Instead, early Earth might have had a regime sometimes called heat pipe volcanism, similar to what we see on Jupiter's moon, Io today, where enormous amounts of heat escape through intense volcanic activity without any organized plate motion. Or it might have had a kind of squishy mobile lid, something intermediate between stagnant lid and full plate tectonics, where chunks of crust moved around in a disorganized way without the clean geometry of modern plate boundaries. The geological record starts to show more convincing evidence of plate tectonic signatures, things like ophiolicites, which are slices of oceanic crust that got shoved up onto continents during collisions, or blue schist metamorphic rocks, which form only under the specific high-pressure, low-temperature conditions found in subduction zones around 2 to 3 billion years ago in the Archean and Proterozoic eons. But even these are debated. The oldest widely accepted ophiolites are about 2 billion years old. The oldest blue schists are roughly similar in age. Some researchers point to structures in rocks from the Barberton Greenstone Belt in South Africa, about 3.2 billion years old, that they interpret as evidence of subduction. Others push back. What most researchers agree on is that even if some form of plate tectonics existed early on, it probably looked quite different from what we see today. The mantle was hotter, maybe 200 to 300 degrees Celsius hotter than now, which means it was less viscous, convection was more vigorous, and plates, if they existed, were probably thinner, smaller, and moved faster. The style of tectonics likely evolved over time as the Earth gradually cooled, and this connects us to something profound about our planet's long-term evolution, because plate tectonics isn't just a geological process. It's deeply intertwined with Earth's climate, its atmosphere, its oceans, and here's where it really gets fascinating, with life itself. The story of plate tectonics is, in a very real sense, the story of why Earth became a place where living things could emerge, survive, and thrive for billions of years. And the key to understanding that connection is a single element: carbon. Let's talk about carbon for a moment, because it's doing something on Earth that it doesn't do on any other planet we know of. And plate tectonics is the reason why. Carbon dioxide is a greenhouse gas, you know this. It traps heat in the atmosphere, keeps the planet warm. Without any carbon dioxide at all, Earth's average surface temperature would be well below freezing. Something like minus 18 degrees Celsius. The oceans would freeze. Life as we know it wouldn't exist. So you need some carbon dioxide. But too much, and you get a runaway greenhouse effect. You get Venus, where the surface temperatures is around 460 degrees Celsius, and the atmospheric pressure is 90 times what we experience on Earth. Venus has a thick crushing blanket of carbon dioxide, and it has no way to get rid of it, because it has no plate tectonics, no subduction, no mechanism to cycle that carbon back into rock. Earth does have that mechanism, and it's elegant in a way that almost feels designed, though it's entirely the product of physics and chemistry operating over deep time. Here's how it works. Carbon dioxide dissolves in rainwater. When rain falls through the atmosphere, it picks up CO2 and forms a weak carbonic acid. That slightly acidic rain hits exposed rock, particularly silicate rocks like granite and basalt, and slowly dissolves them. This is chemical weathering. The dissolved minerals, including calcium and bicarbonate ions, wash down rivers into the ocean. In the ocean, marine organisms, things like foraminifera, coccolithophores, corals, use those calcium and bicarbonate ions to build their shells and skeletons out of calcium carbonate. When those organisms die, their shells sink to the ocean floor and accumulate as layers of limestone and other carbonate sediments. Over millions of years, those sediments ride the conveyor belt of the ocean floor toward a subduction zone. The plate dives down into the mantle, carrying all that stored carbon with it. Deep underground, the heat and pressure break down the carbonate minerals, releasing CO2, which eventually finds its way back to the surface through volcanic eruptions. The CO2 enters the atmosphere again, dissolves in rain again, weathers rock again, gets captured by organisms again, gets subducted again. A cycle, a grand, slow, planet-spanning cycle that takes tens of millions of years to complete one full loop. This is the carbon cycle, or more precisely, the long-term inorganic carbon cycle, sometimes called the carbonate-silicate cycle. And the beautiful thing about it, the thing that makes it so important for habitability, is that it has a built-in thermostat. Think about what happens if the planet gets warmer for some reason. Maybe volcanic activity increases and pumps extra CO2 into the atmosphere. The temperature rises, but warmer temperatures mean more evaporation, more rainfall, faster chemical weathering of rocks. Faster weathering pulls more CO2 out of the atmosphere. The greenhouse effect weakens. The planet cools back down. Now think about the reverse. If the planet cools, maybe volcanic activity decreases. There's less CO2 being added to the atmosphere. But the cooling also means less rainfall, less weathering, and so less CO2 being removed. The CO2 that volcanoes do emit gradually accumulates. The greenhouse effect strengthens. The planet warms back up. It's a negative feedback loop, and it operates over timescales of hundreds of thousands to millions of years. It's not fast enough to counteract the kind of rapid CO2 increase humans are causing today. That's happening on a time scale of decades, and the thermostat takes geological time to respond. But over the long sweep of Earth's history, this thermostat has kept the planet's temperature within a range that's broadly habitable for billions of years. And the engine driving the whole thing is plate tectonics. Without subduction to recycle carbon into the mantle, without volcanic eruptions to release it back, the cycle breaks. the thermostat stops working. This is almost certainly what happened on Venus. Early in its history, Venus might have had liquid water, might have had conditions not so different from early Earth. But without plate tectonics to regulate its hot carbon cycle, CO2 accumulated it in the atmosphere. Temperatures rose. The oceans, if they existed, evaporated. Water vapor is also a greenhouse gas, so that made things worse. Eventually, the water was lost to space. Ultraviolet radiation broke water molecules apart in the upper atmosphere, and the lightweight hydrogen atoms escaped Venus's gravity. Without liquid water, there was no rain, no weathering, no way to pull CO2 out of the atmosphere. The system tipped into a permanent, irreversible greenhouse state. Venus became the hellscape it is today. Same basic ingredients as Earth, roughly the same size, roughly the same distance from the Sun, but without plate tectonics, a completely different outcome. Now, there's another connection between plate tectonics and climate that's worth thinking about, and it has to do with the arrangement of the continents themselves. Remember, the plates are moving, continents drift, and where the continents happen to be at any given time profoundly affects ocean circulation patterns, which in turn affect climate. When continents cluster near the equator, they tend to weather faster because tropical conditions are warm and wet. Lots of rain, lots of chemical weathering, lots of CO2 drawdown. When continents drift over the poles, they can accumulate ice sheets, which reflect sunlight and cool the planet further. The opening and closing of ocean gateways, narrow passages between continents, can redirect ocean currents in ways that dramatically alter heat distribution around the globe. One of the most dramatic examples of this is the opening of the Drake Passage, the stretch of water between the southern tip of South America and the Antarctic Peninsula. For most of the Mesozoic era, when dinosaurs roamed the Earth, and Antarctica was connected to South America and Australia as part of the old Gondwana supercontinent. Warm ocean currents could flow from the tropics down to the Antarctic region, keeping it relatively mild. Antarctica had forests. It had dinosaurs. But starting around 34 million years ago, in the late South America and Antarctica finally separated enough to open the Drake Passage. Once that gateway opened, a powerful ocean current, the Antarctic Circumpolar Current, could flow all the way around Antarctica without being blocked by any landmass. This current effectively isolated Antarctica from warmer waters to the north. The continent cooled dramatically. Ice sheets began to form, and they've been there ever since. The entire climate regime of the southern hemisphere changed because two plates moved apart by a few hundred kilometers. And this kind of thing has happened over and over throughout Earth's history. The closing of the Isthmus of Panama around 3 to 4 million years ago, when the Central American land bridge rose up and connected North and South America, cut off the flow of water between the Atlantic and Pacific Oceans. That redirection of ocean currents is thought to have intensified the Gulf Stream, brought more moisture to northern latitudes, and may have contributed to the onset of the Pleistocene ice ages. The arrangement of continents isn't just geography. It's a climate control mechanism and it's entirely driven by plate tectonics. But let's go even deeper into the relationship between tectonics and life, because this is where things get really profound. Plate tectonics doesn't just regulate climate, it creates habitats. It builds mountains, which create rain shadows and isolated valleys and altitudinal gradients that drive speciation. It opens and closes ocean basins, which separates and reconnects populations of organisms, driving evolution. When Pangaea broke apart, starting around 200 million years ago, populations of animals and plants that had been part of one continuous ecosystem were suddenly isolated on separate continents, drifting apart. They evolved independently. That's why Australia has marsupials and South America had its own unique mammal fauna. Before the Isthmus of Panama allowed North American species to migrate south. The geography of life, biogeography, the field that gave Wegener some of his strongest evidence, is fundamentally a product of plate tectonics. And then there's the role of tectonics in mass extinctions and recoveries. The largest mass extinction in Earth's history, the Permian Triassic extinction about 252 million years ago, which wiped out roughly 90% of marine species and 70% of terrestrial vertebrate species, is closely linked to a massive volcanic event, the Siberian Traps. These were enormous flood basalt eruptions that covered millions of square kilometers of what is now Siberia in lava, and more importantly, released staggering quantities of CO2, sulfur dioxide, and other gases into the atmosphere. The eruptions likely triggered rapid global warming, ocean acidification, and ocean anoxia, oxygen depletion in the seas. And what caused the Siberian Traps? A mantle plume, a massive upwelling of hot material from deep in the mantle, punching through the lithosphere. The same deep mantle dynamics that drive plate tectonics also drive these catastrophic volcanic events. The Deccan Traps in India, another massive flood basalt province, erupted right around the time of the end Cretaceous extinction 66 million years ago, the one that killed the non-avian dinosaurs. Now, the asteroid impact at Chicxulub gets most of the credit for that extinction, and rightly so. But the Deccan eruptions were already stressing ecosystems before the asteroid hit. Some researchers think the impact itself may have even intensified the Deccan volcanism by sending seismic waves through the Earth. The interplay between deep Earth processes and surface life is intricate and sometimes devastating. But tectonics also enables recovery. After a mass extinction, the continued cycling of nutrients, the creation of new habitats through rifting and mountain building, the regulation of climate through the carbon cycle, all of these tectonic processes help life rebound and diversify again. Plate tectonics creates the conditions for both catastrophe and renewal. It's the restless engine that keeps Earth's surface dynamic, keeps the chemistry of the oceans and atmosphere in flux, keeps the planet from settling into a static, dead equilibrium. There's one more connection worth lingering on, and it has to do with something you might not immediately associate with geology: Earth's magnetic field. We talked earlier about how the magnetic field was crucial for proving seafloor spreading. with those beautiful symmetric stripes of normal and reversed polarity on either side of mid-ocean ridges. But the magnetic field itself is generated inside the Earth in the outer core, where liquid iron and nickel convect and create electrical currents through a process called the geodynamo. And here's the thing. The magnetic field is essential for life because it shields the planet from the solar wind, that stream of charged particles constantly flowing outward from the sun. Without the magnetic field, the solar wind would gradually strip away Earth's atmosphere, particularly the lighter molecules. This is probably what happened to Mars. Mars lost its global magnetic field early in its history, likely because its core cooled and solidified, and without that protective shield, the solar wind eroded its atmosphere over billions of years, leaving the thin wisp of atmosphere it has today. Now, the connection between plate tectonics and the magnetic field is indirect but real. Plate tectonics helps cool the mantle, which in turn helps maintain the temperature gradient across the core mantle boundary that drives convection in the outer core. Subducting slabs of cold oceanic lithosphere sink all the way down to the base of the mantle. We can see them in seismic tomography. Remember those fast velocity anomalies piled up near the core mantle boundary. Those cold slabs help extract heat from the core, which keeps the outer core convecting, which keeps the geodynamo running, which keeps the magnetic field alive. It's a chain of connections that stretches from the surface of the planet all the way down to its center. And if you break any link in that chain, the consequences cascade upward. So when you step back and look at the whole picture, plate tectonics isn't just moving continents around. It's regulating the climate through the carbon cycle. It's shaping ocean circulation and weather patterns through continental arrangement. It's driving evolution through the creation and destruction of habitats. It's enabling the magnetic field that protects the atmosphere. It's recycling nutrients from the deep earth back to the surface. It is, in a sense, the operating system of a habitable planet. And this realization has completely transformed how scientists think about what it means for a world to be alive, geologically speaking. Because for most of the 20th century, the search for life beyond Earth was really a question about chemistry. The right molecules, the right temperature, liquid water, and those things still matter enormously. But plate tectonics added a whole new dimension to the conversation, one that planetary scientists are still working through today. Think about it this way. When astronomers started discovering exoplanets in the mid-1990s, the first confirmed one orbiting a sun-like star was 51 Pegasi b, found in 1995 by Michel Mayor and Didier Queloz. The immediate question was always about the habitable zone. That's the band of orbital distances around a star where liquid water could exist on a planet's surface. Not too hot, not too cold, the so-called Goldilocks zone. And that's a perfectly reasonable first filter. If you're looking for life as we know it, you need liquid water. And liquid water needs temperatures in a certain range, and temperature depends heavily on how far you are from your star. Simple enough. But here's the thing. We already knew from our own solar system that being in the habitable zone isn't sufficient. Venus is arguably at the inner edge of the Sun's habitable zone, or at least close to it, and Venus is a hellscape. Mars is near the outer edge, and Mars is a frozen desert with almost no atmosphere. Earth sits right in the sweet spot, and Earth is teeming with life. So clearly, distance from the star isn't the whole story. And as scientists started thinking more carefully about what makes Earth special, plate tectonics kept coming up as this crucial ingredient that the habitable zone concept alone couldn't capture. The reasoning goes something like this. Even if you put a rocky planet at exactly the right distance from its star, with exactly the right amount of water, the planet still needs a way to regulate its temperature over billions of years. Stars get brighter as they age. Our sun is about 30% more luminous now than it was 4 billion years ago. That's a huge change. If Earth had no way to adjust its greenhouse effect in response to that increasing solar output, the oceans would have boiled away long ago, or the planet would have frozen solid early on before the sun warmed up enough. The carbonate-silicate cycle, that thermostat we talked about, is what kept Earth's temperature in a livable range, despite the sun's changing brightness. And that thermostat requires plate tectonics. It requires subduction to carry carbon down into the mantle and volcanism to release it back into the atmosphere. Without those processes, the thermostat breaks. So, when scientists started building models of planetary habitability for exoplanets, some of them began arguing that plate tectonics should be considered almost as important as the habitable zone itself. Not everyone agrees with this. There's a genuine debate, and some researchers think a planet could maintain habitable conditions through other mechanisms, like volcanic outgassing from hotspot volcanism alone, without full-blown plate tectonics. But the idea that plate tectonics is a key factor in long-term habitability has become one of the central questions in astrobiology. And this leads to a really profound and slightly unsettling question. How common is plate tectonics in the universe? Because if plate tectonics is rare, if it requires a very specific set of conditions that most rocky planets don't have, then habitable worlds might be far rarer than the habitable zone alone would suggest. Remember what we talked about with Venus and Mars? Venus is almost the same size as Earth, made of similar stuff, sitting relatively nearby in the solar system, and it doesn't have plate tectonics. Mars is smaller and farther away, and it doesn't have plate tectonics either. In our own solar system, is it the only planet with active plate tectonics, 1 out of 4 rocky planets. That's not a great ratio if you're hoping plate tectonics is common. Now, you might be thinking, well, maybe Earth is just lucky. Maybe we hit some narrow window of conditions, the right size, the right amount of water, the right composition, and most rocky planets miss it. And honestly, that might be true. We talked earlier about how water is crucial for weakening rock and enabling subduction, and how the amount of water matters. Too little, and the rock is too strong, possibly too much, and you get a water world with no exposed continents, and maybe a different style of tectonics or none at all. The planet's size matters too. because it affects how quickly the interior cools and how much internal heat is available to drive convection. A planet that's too small cools too fast, like Mars. A planet that's too large might have such high pressures in its interior that the rock behaves differently, perhaps making subduction harder or easier. We genuinely don't know. The composition of the mantle matters. The radioactive element content matters. Whether the planet had a giant impact early in its history that helped form a large moon and maybe stirred up the interior, that might matter too. There's actually a fascinating line of research suggesting that our moon played a role in Earth's tectonic history. The giant impact hypothesis. The idea that a Mars-sized body called Theia slammed into the early Earth about 4.5 billion years ago, and the debris coalesced into the moon. That impact would have completely melted Earth's surface, creating a global magma ocean. Some researchers think this reset Earth's thermal evolution in a way that was actually favorable for eventually developing plate tectonics. The impact would have also stripped away any early atmosphere Earth had, allowing a new one to form from volcanic outgassing, which might have set up better conditions for the carbon cycle. And the moon's gravitational influence creates tidal forces that flex Earth's interior slightly, which some scientists have speculated could contribute a small amount of energy to mantle dynamics, though this is probably a minor effect compared to the main heat sources. The point is, when you start listing all the factors that might be necessary for plate tectonics, the list gets long, and each factor narrows the odds. This is related to a broader idea in astrobiology, sometimes called the rare earth hypothesis, proposed by Peter Ward and Donald Brownlee in their 2000 book of the same name. Their argument was that while simple microbial life might be common in the universe, complex multicellular life like animals and plants requires such a specific set of planetary conditions, including plate tectonics, a large stabilizing moon, a magnetic field, the right kind of star, a position in the galaxy away from too much radiation, that planets like Earth might be extraordinarily rare. It's a sobering idea, and plate tectonics sits right at the heart of their argument. Not everyone buys the rare Earth hypothesis, of course. Some scientists think life is more adaptable than we give it credit for, that there might be alternative pathways to habitability that don't require plate tectonics specifically. Maybe a planet with vigorous volcanic activity from mantle plumes could cycle enough carbon to maintain a stable climate. Maybe life could thrive in subsurface oceans, like those on Europa or Enceladus, where plate tectonics in the traditional sense isn't happening. But tidal heating provides energy, and liquid water exists beneath ice shells. These are open questions, genuinely open, and they're driving some of the most exciting research in planetary science right now. What's beautiful about this is how it brings the story full circle. We started with Abraham Ortelius in the 16th century, noticing that the coastlines of continents seem to fit together, and Alfred Wegener being ridiculed for suggesting they actually moved. We traced the painstaking accumulation of evidence through the 20th century. Marie Tharp Mapping the ocean floor, Harry Hess imagining sea floor spreading, the magnetic stripes confirming it, Tuzo Wilson, and Dan Mackenzie, and Jason Morgan building the mathematical framework. And now, in the 21st century, plate tectonics has become central to one of the biggest questions humanity has ever asked. Are we alone? The same theory that started as a controversial idea about drifting continents is now shaping how we design space missions, how we choose which exoplanets to study, and how we think about the conditions for life in the universe. And the tools keep getting better. The James Webb Space Telescope, which began science operations in 2022, can analyze the atmospheres of exoplanets by looking at the starlight that filters through them during transits. If a rocky planet in the habitable zone has an atmosphere with certain combinations of gases, carbon dioxide and water, vapor carbon cycle, or oxygen and methanes in disequilibrium suggesting biological activity, that could be indirect evidence that something like plate tectonics is operating. We can't see tectonic plates on a planet dozens of light years away, obviously, but we might be able to detect their atmospheric fingerprints. Meanwhile, back here on Earth, the science of plate tectonics itself continues to evolve in ways that would astonish the founders of the theory. Seismic tomography has gotten dramatically more detailed. Dense seismic arrays, networks of hundreds or even thousands of seismometers deployed in tight grids, are revealing the mantle's structure at resolutions that were unimaginable a few decades ago. The U.S. Array Project, part the Initiative, part the EarthScope Initiative, of 400 rolling broadband seismometers across the continental United States between 2004 and 2015, moving the grid westward to eastward like a wave. The images it produced of the mantle beneath North America are stunning in their detail. You can see the subducted Farallon Plate, that ancient oceanic plate that's been diving under North America for over 100 million years, still sinking through the mantle, broken into fragments, some of them draped across the transition zone at 660 kilometers depth. You can see the Yellowstone plume, a column of anomalously hot material rising from deep in the mantle. These images are transforming our understanding of what's happening beneath our feet right now, in real time, on geological timescales. And there's something else that's changed profoundly in recent years, something that connects plate tectonics to a much more immediate human concern than the search for extraterrestrial life. It has to do with earthquakes, and specifically with our ability to understand, and maybe, just maybe, someday anticipate them. Because for all the elegance of plate tectonic theory, for all its explanatory power, there's one thing it hasn't yet given us that people desperately want: reliable earthquake prediction. And the story of why that's so hard, and what we've learned from trying, is one of the most humbling chapters in the entire history of this science. Because here you have a theory that explains why earthquakes happen, where they happen, even roughly how often they happen along a given fault, and yet, when you ask the honest question, will there be a major earthquake in this city next week, next month, next year? The answer, even now, even with everything we know,
is we can't tell you.
Not with any useful precision. And understanding why we can't tell you turns out to be just as fascinating as the theory itself. Let's start with what plate tectonics does tell us about earthquakes, because it tells us a lot. We know that the vast majority of earthquakes occur at plate boundaries. We know that subduction zones produce the most powerful earthquakes on the planet, magnitude 9 and above. We know that transform faults like the San Andreas produce frequent, damaging quakes. We know that the collision of India with Asia is responsible for the seismicity of the Himalayas and the devastating earthquakes that periodically strike Nepal, Pakistan, and Western China. We can even calculate the long-term slip rate of a fault, how fast the plates on either side are moving relative to each other, and from that, estimate how much strain is accumulating over time. The San Andreas Fault, for instance, accommodates roughly 35 to 46 millimeters of motion per year between the Pacific and North American plates. We know that. We can measure it with GPS now, down to fractions of a millimeter. So here's the thing. If you know how fast strain is building, and you know roughly how much strain was released in the last big earthquake, and you know the date of that last big earthquake, you might think you could calculate when the next one is due, and in a very rough statistical sense you can. This is the concept of the seismic gap, the idea that segments of a fault that haven't ruptured in a long time are more likely to rupture soon because they've been accumulating strain. It's a reasonable idea. It makes physical sense. And in broad terms, it works. The Cascadia subduction zone off the Pacific Northwest coast, for example, we know from geological evidence, from buried forests and tsunami deposits, that it produces magnitude 9 earthquakes, roughly every 200 to 600 years, and the last one was in January 1700. So we know another one is coming. We just don't know if it's coming in 50 years or 300 years. That's a pretty wide window, and this is where the dream of earthquake prediction crashes into the reality of how faults actually behave. Because faults are not clocks. They don't store up a precise amount of energy and then release it on a predictable schedule. The physics of friction along a fault surface is extraordinarily complex. The fault isn't a clean, smooth plane. It's a rough, irregular surface with patches of different strength, different mineral composition, different amounts of fluid pressure in the pore spaces of the rock. Some patches might creep slowly and continuously, releasing strain without any earthquake at all. Other patches are locked, stuck, building up enormous stress that will eventually release in a sudden, violent rupture. And how those patches interact, how the failure of one patch transfers stress to its neighbors, potentially triggering a cascade, that depends on details of the fault's geometry and material properties that we simply cannot map at the necessary resolution. Not from the surface, not with current technology. There was a period, particularly in the 1970s and 1980s, when earthquake prediction seemed tantalizingly close. The Chinese scored what looked like a dramatic success in February 1975, when authorities in Haicheng, in Liaoning province, ordered an evacuation based on a series of foreshocks and other precursory signals. Changes in groundwater levels, unusual animal behavior, small earthquakes increasing in frequency. Hours later, a magnitude 7.3 earthquake struck. The evacuation saved thousands of lives. It was hailed as a triumph of earthquake prediction. But here's the kicker. Just 17 months later, on July 28, 1976, a magnitude 7.5 earthquake struck Tangshan, an industrial city about 400 kilometers to the southwest. With essentially no warning, the death toll was catastrophic. Official Chinese figures eventually put it at around 242,000, though some estimates run much higher. It was one of the deadliest earthquakes in recorded history. And it came without the foreshocks, without the precursory signals that had preceded Haicheng. The Haicheng success, it turned out, was partly skill but largely luck. That particular earthquake happened to be preceded by an unusually clear foreshock sequence, which most large earthquakes simply don't produce. In the United States, a similar arc of hope and disappointment played out. In the late 1970s and 1980s, the U.S. Geological Survey invested heavily in monitoring a segment of the San Andreas Fault near Parkfield, California, a small town in the Coast Ranges. Parkfield had experienced moderate earthquakes around magnitude 6 at remarkably regular intervals: 1857, 1881, 1901, 1922, 1934, and 1966. The average interval was about 22 years. So scientists predicted the next Parkfield earthquake would occur around 1988, give or take a few years. They instrumented the area intensively. Seismometers, strain meters, creep meters, GPS stations, everything they could think of. And they waited. 1988 came and went. 1990, 1995, 2000. The earthquake finally arrived on September 28, 2004. 16 years late. And when it came, none of the instruments detected any clear precursory signal. The earthquake just happened. The data were scientifically valuable, enormously so, but as a prediction experiment, Parkfield was a sobering lesson. Now, you might be thinking, well, we just need better instruments, more data, more computing power. And there's some truth to that. We are getting better data all the time. But there's a deeper issue, and it has to do with the fundamental nature of the system. Earthquake faults may be what physicists call a self-organized critical system. Think of it like a sand pile. You drip sand onto a pile, grain by grain, and the pile builds up, getting steeper and steeper. Every now and then a grain lands and triggers an avalanche. Sometimes it's a tiny avalanche, a few grains sliding. Sometimes it's enormous. A significant fraction of the pile collapses. And here's the crucial insight. The grain that triggers the big avalanche looks exactly like the grain that triggers the small one, or the grain that triggers nothing at all. The difference isn't in the trigger. It's in the state of the pile at that instant, the precise arrangement of every grain, every contact, every tiny arch and void. And that state is, for all practical purposes, unknowable in sufficient detail. Faults may work the same way. The stress field along a fault is the sand pile. Small earthquakes are small avalanches. Large earthquakes are large avalanches. And the difference between a small earthquake that stops and a small earthquake that cascades into a catastrophic rupture may depend on details of the stress and strength distribution along the fault that are below our ability to measure. This doesn't mean prediction is theoretically impossible. It means it may require a level of knowledge about the subsurface that we're very, very far from achieving. But here's what's really interesting and genuinely hopeful. While prediction, telling you a specific earthquake will happen in a specific place at a specific time, remains elusive, something else has emerged that's arguably more useful in the near term. It's called earthquake early warning, and it's a completely different approach. Instead of trying to predict earthquakes before they happen, early warning systems detect earthquakes the moment they begin and send alerts to people farther away, say before the damaging waves arrive. This works because electronic signals travel at the speed of light while seismic waves travel through rock at a few kilometers per second. If you have a dense network of seismometers near a fault, and one of them detects the initial P wave, the fast but relatively gentle compressional wave that arrives first, you can calculate the earthquake's location and magnitude within seconds and send a warning to cities farther away before the slower, more destructive S waves and surface waves arrive. Japan's system, developed after the devastating 2011 Tohoku earthquake and tsunami, is the most advanced in the world. The Shake Alert system in the western United States went public in 2019 and has already provided seconds to tens of seconds of warning for several significant earthquakes. It's not prediction, but those seconds matter. Enough time to duck under a table, for a surgeon to lift a scalpel away from a patient, for trains to begin braking, for automated systems to shut valves in gas pipelines. And this brings us to something worth sitting with for a moment. Plate tectonics, as a theory, is barely 60 years old. In the span of human knowledge, that's nothing. Think about where we started. Abraham Ortelius in 1596, noticing the shapes of the continents, wondering. Alfred Wegener in 1912, assembling his evidence, being ridiculed. Marie Tharp in the 1950s, mapping the ocean floor, seeing the Rift Valley, being told it was girl talk. Harry Hess, quietly proposing seafloor spreading. Vine and Matthews, decoding the magnetic stripes. Tuzo Wilson drawing the first transform faults on a napkin. Dan Mackenzie and Bob Parker working out the mathematics on a computer the size of a room. Jason Morgan dividing the world into rigid plates. Xavier Lepichon building the first complete global model. All of that, the entire intellectual revolution, happened within a single human lifetime. Someone born in 1910 could have lived through the entire thing, from Wegener's continental drift being dismissed as a fantasy to plate tectonics being the unifying framework of Earth science. And what that framework revealed is something genuinely profound. The ground beneath your feet. The ground that feels so solid and permanent is moving. It has always been moving. The continents you see on a map are just the current arrangement, a snapshot in a 4.5 billion-year-long dance. 200 million years ago, you could have walked from New York to Casablanca without getting your feet wet. 1 billion years ago, the continents were assembled in a configuration we can barely reconstruct. 1 billion years from now, the Atlantic Ocean may have closed. The Americas and Africa and Europe may have merged again into some new supercontinent that doesn't have a name yet, though some geologists have started calling it Pangaea Proxima or Amasia, depending on which model they prefer. And the thing that moves those continents, convection in the mantle, that slow churning of hot rock driven by Earth's internal heat, that same process is what gives us our atmosphere, our oceans, our magnetic field, our climate stability. It's what recycles carbon. It's what builds mountains that weather and pull CO2 from the air. It's what creates the volcanic gases that replenish what's lost. It's what generates the magnetic field that shields us from the solar wind. Take away plate tectonics, and you don't just get a geologically boring planet. You might get a dead one. Venus might be the proof of that. So when you lie here, feeling the stillness of the night, feeling the solidity of the ground beneath whatever building you're in, know that it's not really still. Beneath you, right now, the mantle is convecting. Plates are moving. Somewhere in the Pacific, oceanic crust is sliding into a trench at the rate your fingernails grow. Somewhere in Iceland, new crust is being born as magma wells up to fill the gap where two plates are pulling apart. Somewhere deep in the mantle, a plume of hot rock that started rising before humans existed is still on its way up, carrying heat from near the core towards the surface. And when it arrives, in a few million years, it will punch through the crust and build new volcanoes that no one alive today will ever see. The Earth is alive in a way that no other planet in our solar system is. Not alive in the biological sense, though it supports that too, but alive in the geological sense, dynamic, restless, constantly remaking itself. And the beautiful thing, the thing that might be worth carrying with you as you drift off, is that we figured this out. Humans with seismometers and magnetometers and research ships and mathematics and stubbornness and curiosity. We figured out that the world is not what it appears to be. The continents move, the ocean floors are young, the mountains are temporary, and all of it is connected. The earthquakes and the volcanoes and the climate and the magnetic field and the very air you're breathing right now, with its oxygen and its carbon dioxide held in a balance that depends, ultimately, on the slow, patient, powerful motion of rock beneath your feet. That's plate tectonics. That's the story of the ground you're lying on. And it's still being written right now, 1 millimeter at a time, while you sleep.